All right, kids, we're looking at section 5.9 today. It's a lot like 5.8 was, but this time we're going to look at it from a more algebraic perspective rather than a graphic perspective. So we're connecting the function with the first derivative with the second derivative. Again, the original function, this is telling you increasing, decreasing, positive slopes, negative slopes. This is telling you concavity, concave up, concave down, happy face, sad face kind of stuff. All right, so for the function f of x, they give you the function. Use a table to help you organize and draw conclusions. So they want to know, ultimately, we're going to get to, when is the function both concave up and decreasing? Well, concave up comes from the second derivative, decreasing comes from the first derivative. So what we need to do is make a sign chart out of both of these things. So if I'm going for the first derivative, I'm looking for the critical points. My critical points come from setting that first derivative equal to 0 and solving it out and then figuring out if there's any undefined places. So first derivative, 6x squared plus 8x plus 2 equals 0. Well, I can see everybody's got a 2. I'm going to take that out. So I've got 2 parentheses 3x squared plus 4x plus 1. And then that gets set equal to 0. 2 equals 0 doesn't happen. That disappears. But believe it or not, this guy actually factors. This guy factors into 3x plus 1 and x plus 1. So in other words, I've got x equals a negative 1/3 and x equals negative 1. Is there anywhere where I'm undefined? And I'm a cubic function, so there's nowhere that's going to be undefined. All right, so let's put these on our chart. This is our first derivative chart. I have negative 1/3. I have 1. Oh, negative 1. Actually, they should be switched, right, if I'm doing them in order. So negative 1 is smaller. So I'm putting negative 1. Let me fix that. Negative 1 goes on the left, negative 1/3 on the right. I'm going to pick values and I'm going to plug them into the first derivative. You can put them into either, well, any of these three, but I'm going to go for this guy. If I am left of negative 1, could I not pick, actually I want to go this way. If I'm left of negative 1, let's go negative 2. Negative 6 plus 1 is negative 5. Negative 1, so negative negative makes this positive over here. A little tricky in between, right? Because I'm in between here, these two things. Maybe negative 2/3. Negative 2/3 is going to give me a negative here, negative 2/3, and a positive here. So negative positive makes this negative. If I put in 0, always love 0, I get a positive, positive, and so positive. So there's my sign chart for this guy. So I can tell it's decreasing from negative 1 to negative 1/3. Now, over here, it's talking about my concavity, my second derivative. So I'm going to take my first derivative here. I'm going to find the second derivative. It is 12x plus 8. Set that equal to 0. Make my sign chart off of this. 12x equals 8. X equals 8/12. A couple different ways I could have done this, but nonetheless, this was a negative 8, negative. So that makes this a negative 2/3. 4 goes into those. So I only have one thing to put on this, negative 2/3. Into my second derivative, I'm going to put numbers to the left and to the right. So if I'm left of negative 2/3, I can put 0 in. That gives me a positive. Actually, let's see, negative 2/3. No, 0's over here. Why am I being silly? Negative 1, put negative 1 in. Negative 1 gives me a negative 12, positive 8 gives me a negative. If I put 0 in, that's over here, that's going to be a positive. Okay. Where is this thing both concave up and decreasing? Concave up and decreasing. Here's how I kind of like to do it. They do, the curriculum people do it just slightly differently, slightly different than I would do it. But here's what I would do. I'm going to combine these two sign charts. So hopefully there's enough space here to do this. I'm putting my 3 values onto my sign chart. So I have a negative 1 is furthest to the left. Then I have a negative 2/3. And then I have a negative 1/3. And so what I'm going to do is I'm going to put both of those sign charts, and you'll see when I do problems below, I'm just going to make the one sign chart. But I've got, I'm going to put the first derivative on top, and I'm going to put the second derivative on the bottom of this same sign chart. So it goes to the left of -1 is positive. Between -1 and -1/3 is negative. So this whole part is negative. Notice I wrote that twice, negative for this. And then it changes positive over here. And so there's my first derivative chart. Let me take my second derivative chart. I'm going to put him in a different color down below. And that means that to the left of -2/3 is negative. So this is negative, this is negative. To the right of -2/3, I have positives. This is positive, this is positive. And so for me, looking at where it's both concave up and decreasing, concave up, I want the second derivative to be positive, and I want to be decreasing the first derivative to be negative. So where on my sign chart do I have a negative first derivative and a positive second derivative? Oh, I can see that the only place that that happens is right in here. And so that's my answer. So for me, I don't like putting them separate. I like making one combined thing to be able to answer this question. So to finally answer the question, where is it doing both? And we would say that that would be between -2/3 and -1/3. That would be my answer for this question. When is the function both concave up and decreasing? Between -2/3 and -1/3 on our sign chart. That's it. Now a lot of times they'll ask you questions about, is this thing speeding up or slowing down? So let's remember again about how that works. We've done those before. An object is speeding up if the velocity and acceleration have the same signs. And it's slowing down if my velocity and acceleration have different signs. So I'm comparing first derivatives and second derivatives. Takes me to number 2. A particle is moving along the x-axis with this position function. Find the velocity and acceleration functions and describe the motion of the particle. So, in other words, they want to know when is it speeding up, when is it slowing down, and so forth. So, if I find the velocity first, all right, take the derivative. 3 comes down, 3 times 1/3. So I've got t squared. I've got minus 8t plus 12. My acceleration, take the derivative of that, 2t minus 8. I want to describe the motion. Well, that means I need to figure out what the sign charts are doing so I know when it's moving which way and how it's speeding up or slowing down. So I'm going to set these equal to 0. I'm going to hope they factor, and they do. Sweet. So I have a t minus 6, and I've got a t minus 2. So I get t equals 6, t equals 2. And then over here, I've got, when I set him equal to 0, 2t minus 8. I know 2t equals 8, so t is 4. So if I put these together on a combined sign chart, which they weren't really specific on the motion, they're not necessarily looking for, we're going to be more specific to say when is it speeding up or slowing down based off the box up above, rather than moving left or right on this thing. So let's make a sign chart. Sign chart, this is a combined sign chart because I need to compare the first derivative and the second derivative. So up top is going my first derivative, down the bottom is going my second derivative. And so I have a value of 2, 4, and 6. So here's 2. This guy, the 4, is coming off the second derivative, not that it matters much. And then I have a 6. Let's do first derivative first. If I am at 0, I'm a negative times a negative, therefore I am positive. If I'm between 2 and 6, I can pick any number I want. I can even pick the 4. So negative 2, positive 2, this would be a negative. And it stays negative over here, remember, because it's 2 and 6 are my critical points. But you could take 5 and plug it in and see that it really does come out to be a negative. If I pick a number beyond 6, like 10, I get positive, positive, this is positive. All right, let's go for the second derivative and see what happens. Here's my second derivative. Plug in a 0, I get a negative out. If I plug in a 3, it's only going to change at 4, so this, you know that this piece is also going to be negative. If I put in something to the right of 4, like 6, I get 12 minus 4, so now it's positive, and it stays positive the whole rest of the time, because the only switch it can have is at 4. So you see how you have like a double combined, can you see me? I'm looking at my screen and seeing that you're not seeing me. The only place that I can have a this combined kind of thing, it makes it so much easier for me to tell what it's doing. So I know they're actually asking about speeding up and slowing down. Let's see, speeding up and slowing down. What's the first thing it's doing? From, now this is a time situation, right? I guess you could, they weren't very specific. But anyway, we'll say negative infinity to 2. They have different signs, so they're slowing down. So negative infinity to 2, it's slowing down. Then in here, they have the same signs, 2 to 4, they're both negative. That's speeding up. Then they have different signs from 4 to 6, slowing down. Then they have the same signs for the rest of the time, from 6 to infinity. And so with that combined sign chart, it just makes it really easy. Again, the curriculum folks like to do it separately. For me, I like to put it combined. Either way is absolutely fine, whatever makes you happy. All right, here comes the next kind. Number 3, this is the last practice problem, and then we'll do a couple examples and call it a day. So it says for the given function, f of x, f prime of x, and f double prime of x do not change signs. A table of values for f of x is given in the table below. The question wants to know, A, is f of x increasing or decreasing? So there's a couple different ways I'm going to show you that you can look at this. And I'm going to show you 2 different ways because it depends on, like, there's one question that comes up that you have to think about the slopes. You can't do it in the alternate way I'm going to show you in a second. So if I think slopes, if these are my coordinates, and I think about what the slope is, f prime of x. If I think of my slopes, this would be 2 minus 1 over 1 minus 0. So I would have a slope in here that is 1. If I take the next set, you see what I'm doing? Y2 minus y1 over x2 minus x1, 4 minus 2 over 2 minus 1 gives me a slope in here of 2. If I do the next one, 7 minus 3 is 4, 4 minus 2 is 2, 4 over 2, oh, was that right? 4 over, hang on a second, 4 minus 2 is 2 over 1, yeah, that was 2. 4 over 2 is 2. Why did I say it was 3 on my notes? Anybody got a clue? Seven minus 3 is 4. 4 minus 2 is 2. I don't know. Anyway, so if I'm looking at this, I'm looking at my slopes, I can see they're getting bigger, right, from 1 to 2, but it stays the same at 2, so it kind of levels out my slope. But if I look at this, my slopes are increasing. I'll put it this way, according to the table. So is f of x increasing or decreasing? Remember, increasing and decreasing comes off of your first derivatives, and we're going to say increasing because my slopes are positive. Or in other words, I could say my f prime of x are positive. Is it concave up or concave down? Looking at this, if I'm concave up, if I'm increasing, increasing, I must be concave up for this. Now, if you're not sure of these things, here's what I was thinking. Here's my alternate way I was talking about. Plot the points, right? Do a rough plot. Here's my 0, here's my y, 0, 1. Just a rough plot. 1, 2. 2, 4. 3, 7. If I were to connect them together, that's what this function looks like, and therefore I can see it's increasing, and I can also see it's concave up. So if you're not sure, plot the points. They're taking you through this thinking about the slopes because of the derivative type approach. But you can, for this particular type of thing, you can just actually plot the points and then be just as good to go. All right, couple problems to try together, and then we will call it a day. The first one I know I chose was number 5. Same kind of questions. Is this increasing or decreasing? And so they want us to think slopes. Let's see if I've got it here. 0 minus 3 is negative 3 over 1, gives me a negative 3. Negative 2 minus 4 is negative 6 over negative 3. Negative 6 over negative 3 is 2. And then I have a slope here. Negative 3 minus 5 is negative 8. And negative 8 over, write it out, negative 8 over negative 2 minus 4 and negative 6 gives me a positive 4/3. 4/3. Okay. What can you tell me about your slopes? I've got slopes over here, and maybe let's, again, if I'm taking the alternate route on this thing, looking at the coordinates 2, 3, 3, 0, 4, negative 2, and 5, negative 3. So my picture goes like this. So I can see that that I've got my slopes here. This is a decreasing function, so my function is decreasing. I don't know that I love this explanation over here so much, finding the slopes of those things. I kind of prefer just to draw out the points. So what they're saying to you is my slopes of the lines are actually getting bigger. Well, start at negative 3. So negative 3 slope, look at the slope of the tangent line would be this way, right? Pretty strong slope. But my slopes keep getting smaller as I go along here. My slope now is 2, and then it's negative 4/3, or it's positive 4/3. So my slopes are getting kind of smaller as I go. My slopes are decreasing. It's kind of confusing when you look at it this way, but if you think of it graphically, this has a stronger slope than this would over here at this place, which has a stronger slope from what this guy would be. So the slopes are decreasing. Easier to see in a picture than it is to read off of that. But is it concave up or concave down? You can see from the picture it is concave up. And so there's your number 5. Number 6 was next on my list. Given the function, find the intervals when g is concave up and increasing at the same time. So this is one of those joint sign charts that we want to do. Let's find the first derivative. Let's find the second derivative. This is a nice quartic function. There's no undefined places. So here I go. Negative 4x cubed plus 4x. Second derivative is negative 12x squared plus 4. Set them equal to 0. That cube scared me in the beginning, but not that bad because I can take out a negative 4x. Leaves me with x squared minus 1. So I get x equals 0, and I get x is plus or minus 1. This guy gives me 0 equals negative 12x squared plus 4. Take out a 4, actually a negative 4, gives me 3x squared minus 1. Oh, that's a little ugly, right? The negative 4 doesn't mean anything, but 3x squared minus 1 gives me an x that is plus or minus the square root of 1/3, right? Swing the 1 over, divide by 3, take the square root. Well, that's not very pretty, but let's put our sign chart together. I have a 0, I have a 1, and a negative 1. The square root of a positive 1/3 is going to be in between there. Maybe I should make these, let me make these my 1/3. All right, there's my positive and negative 1/3, and then here's my negative 1 and my positive 1. Up top, I'm putting my first derivative sign chart, and down the bottom, I'm going to put my second derivative sign chart for this guy and this guy. Let's try it. If I put in a value, let's do the first derivative one first. So if I take a number in between 0 and negative 1, like say, actually I need to go to the left of this too. So if I go negative 2, that's positive and positive. So I'm looking at my first derivative, it's positive. Let me move this over. All right, if I go in between negative 1 and 0, like negative 0.5, when I put that in, I get a positive and a negative, and so I end up with a negative for both of these until I get to 0. And then if I put in a positive 0.5, now I have a negative and I have a negative, that's going to make this positive until I get to 1. And then when I'm to the right of 1, I am putting in a 2, and I have a negative times a positive, so now I'm back to negative. So there's my first derivative sign chart. If I go second derivativing with this thing, it is changing signs at these square root places. So if I go to the left and put in something like negative 0.5 again, let me double check and make sure that that's going to work. What is 1 divided by 3, and then to the 0.5 to the square root. So 0.57. Okay. So we need to go 0.6 on this one. I don't know if you can see that on the screen, but anyway, this comes out to be 0.577. So I need something to the left and to the right of that. So if I go to the left, I'm looking at negative 0.6. If I put a negative 0.6 in, and you can use your calculator to help you with that, but it actually comes out to be a negative. So these are negatives. Everything's negative to the left of that. If I put something in between there, then I can use the 0.5. That's going to actually be positive. It gives me positive until I come here again where I need to change or possibly change. If I put in a positive 0.6, this is going to be back to negatives and negatives. And again, you can use your calculator to help you figure out those values. Plug it in. I would plug in your derivative into your y1 and then go to the table, and you can input whatever values you want to make it a little quicker. All right, now I can answer any question they give me about this. Where is it concave up, second derivative positive, and increasing, first derivative positive? Let's read the graph. I want positive, positive. Nope, 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 yup. Nope, and nope. So the only place where this guy has concave up and increasing is between 0 and a positive square root of 3. 0, positive square root of 1/3, that is. This is where it is concave up and increasing at the same time. Okay, so just kind of reiterating what we talked about in the earlier problems. Last one, number 10. Number 10. I thought this could confuse you, so I chose this guy. Number 10. In the xy plane, the graph of a twice differentiable function, double derivative, it's happy up to its second derivative, y equals f of x, is concave down on the open interval from 1 to 3, concave down, and is tangent to the line y equals 4x plus 3 at x equals 2. Which of the following statements must be true about the derivative? All right, so let's think about what this looks like. 1 to 3. 1, 2, 3. It is concave down. All right? Concave down. Does it matter where it is? No. And there's a tangent line at x equals 2. And that tangent line is y equals 4x plus 3. Well, what's the slope of the tangent line? Slope is 4. Okay. So let's see if we can figure out what the answer for this guy is. The first derivative, the slope, is constant between 2 and 2.1. Well, I kind of didn't draw this very well, but think about it if I were to zoom in on this. If I'm at 2 and then I go to 2.1, a little bit past it, do they have the exact same slopes? And the answer is no, so that's not going to happen. Is my first derivative positive on the interval between 2 and 2.1? Is the first derivative, is my slope positive in both of those locations? And this one's a possibility. I want to think about that one. Is my slope negative? No, negative slopes go the other way, so this is a no. Is my slope greater than 4 on this thing? Well, if I'm 4 at this location, is my slope increasing? Is it getting bigger when I get to the next location, to 2.1? And that would be a no. Last one, E. Is my slope less than 4? Is my slope getting smaller as I look at this thing? And the answer to that is, yeah, it's getting smaller. If I think of my tangent lines, my tangent line here, my next tangent line has a smaller slope than what it did at 4. So is my slope greater than 0? I don't think so. This one, this E is the one that you're looking for. So E is the last one. My slopes are less than or equal to 4, looking at the points between 2 and 2.1. All right, that takes care of section 5.9. I will see you again for 5.10. Shoot me an email if you've got a question, and I'll see you in class.